Have you ever tried to build a giant Lego castle without the instructions? It can be fun, but you might end up with a wobbly tower, missing pieces, and a dragon that looks more like a duck. Building a computer system is a lot like that, but way more complex. Information systems are the digital brains of our world. They handle everything from your online pizza order to a hospital's patient records. If we just start throwing code and computers together without a clear plan, we'd get a digital mess. That's why having a structured process, a kind of master instruction manual, is so incredibly important. It's our roadmap to success. Organizations, just like people, learn and get better. Building complex software can be a bit messy, but that's where a cool idea called the Capability Maturity Model, or CMM, comes in. The CMM is like a growth chart for an organization's software building skills. It shows how an organization can mature from chaotic to disciplined. Level 1, Initial. This is the Wild West of software development. There are no consistent rules. Success depends entirely on a few heroic programmers who work day and night. When they leave, the knowledge leaves with them. Level 2, Repeatable. The organization has learned from past mistakes. They introduce basic project management, finally writing down the recipe. Level 3, Defined. The organization creates a company-wide cookbook, a single standard process for all software projects. This creates consistency and high quality across the entire organization. Level 4, Managed. The organization begins to measure everything. They can predict problems before they happen. Level 5, Optimizing. The organization uses all that data to continuously improve. It's a state of continuous improvement and excellence. When we talk about building systems, you'll hear two important terms: system lifecycle and system development methodology. They sound similar, but they play very different roles. Think of it like building a house. The system lifecycle is the fundamental set of phases that every house must go through: dreaming up the idea, designing the blueprint, gathering materials, building it, and living in it and maintaining it. These phases are universal. Whether you're building a birdhouse or a skyscraper, it's the what we need to do. The system lifecycle is a very high-level conceptual model. Now, a system development methodology is the how. If the lifecycle is the what, the methodology is the specific detailed plan of action for navigating those phases. One builder might use a waterfall methodology, where they completely finish the foundation before starting the walls. Another builder might use an agile methodology, where they build one room completely and let the family move in while they start the next room. Both are building a house, but their approaches are very different. So, a methodology provides the specific rules, tools, techniques, and procedures for each phase of the life cycle. Building a great information system is part science, part art. But like any good science experiment, it helps to follow some fundamental principles. These are not rigid laws, but guiding ideas that help us make smart choices and avoid common pitfalls. They are the collected wisdom of thousands of developers who have learned things the hard way. First, the system is for the users. Always involve the people who will actually use the system. Their input is gold. Second, use a problem-solving approach. Don't just build something cool. Identify a problem and solve it. Third, establish phases and activities. A project without a clear roadmap is a project destined for a detour. Fourth, establish standards for consistent development and documentation. Fifth, justify systems as capital investments. An information system costs time and money, so it should provide a real return on that investment. It needs to improve efficiency, cut costs, or create new opportunities. Sixth, don't be afraid to cancel or revise the scope. Sometimes a project isn't working out. It's smarter to stop or change course than to throw good money after bad. Seventh, divide and conquer. Break a large, complicated system down into smaller, simpler subsystems or modules. This makes the problem easier to understand, easier to build, and easier to test. Eighth, design systems for growth and change. The world isn't static, and neither are businesses. A system built today should be flexible enough to adapt to the needs of tomorrow. Ninth, plan your work, then work your plan. Create a detailed project plan before you start, and then use that plan to guide your work. And 10th, communicate and cooperate. A system is built by a team of people. Constant, clear communication between users, managers, and developers is the secret ingredient that makes everything else work. So, a system development project doesn't just appear out of thin air. There's always a trigger. These triggers fall into three categories: problems, opportunities, and directives. A problem stops the organization from achieving its purpose. It's something broken or not working well. An opportunity improves things even with no specific problem. It's about making something good better. Innovation. A directive is a requirement from management, government, or external forces. You don't have a choice. That's where the PIECES framework comes in. PIECES is a handy acronym, PIECES, that helps us categorize the problems, opportunities, and directives we find. It gives us 6 key areas to look at, ensuring we don't miss anything important. It's like a checklist for a detective trying to solve a case. The P in PIECES stands for performance. This is all about speed and efficiency. A classic performance problem is a website that takes too long to load a page. The I is for information and data. This category deals with the quality and availability of information. A problem here would be managers getting sales reports that are a week old and contain errors. E stands for economics, and it's all about money. This category looks at costs and benefits. A common economic problem is a system that requires too much manual data entry, wasting valuable employee time. The C is for control and security. This is a big one. It's about protecting the system and its data from harm or misuse. A problem would be discovering that unauthorized employees can see sensitive salary information. E is for efficiency, and S is for service. Efficiency is about making the most of our resources, people, time, and technology. For example, having to print a form, get it signed, scan it, and then email it is very inefficient. The S for service is about the value the system provides to its customers, suppliers, or users. An opportunity could be to add a 24/7 online chat feature to improve customer service. Together, Pieces helps us get a complete picture of why a new system is needed. Every information system goes on an epic journey from a tiny spark of an idea to a fully functioning tool used by hundreds or thousands of people. Think of it as a relay race, where each runner passes a baton to the next. The first phase is planning. Here, we identify the project's scope, goals, and feasibility. The input is the initial problem, opportunity, or directive we talked about. We do a quick investigation and produce the output, a project proposal and a plan, which gets passed to the next phase. The baton is passed to the analysis phase. This is where we play detective. The main goal is to understand the existing system and figure out exactly what the new system needs to do. We conduct interviews, study documents, and observe people at work. We ask lots of questions. The output of this phase is a crucial document called the System Requirement Specification. With the what clearly defined, we move to the design phase. Here, we figure out how the system will do it. We design the user interface, the databases, the network architecture, and the software modules. The output is the technical design specification, a complete set of diagrams and plans that programmers can use to actually build the system. Next comes the action-packed implementation phase. This is where the system is actually built, tested, and installed. Programmers write the code, database administrators build the databases, and hardware is purchased and set up. Finally, the old system is turned off, and the new system is turned on. This phase also includes training the users, but the journey isn't over. The final phase is maintenance. Over time, things change. Users might find small bugs, the government might issue a new regulation, or the business might need a small enhancement. The maintenance phase is all about keeping the system running smoothly, fixing problems, and making improvements. This is often the longest and most expensive phase of a system's life. Building a massive information system today is not like it was 30 years ago. Back then, it was like building a skyscraper with handsaws and hammers. Now, we have power tools. In the world of system development, these power tools are sophisticated software programs that automate, manage, and speed up the entire process. CASE stands for Computer-Aided Software Engineering. That's a fancy name, but the idea is simple. CASE tools are software programs that help us with the planning, analysis, and design phases of our project. Think of them as a digital toolkit for architects and planners. Some CASE tools help us draw diagrams, like the data flow diagrams we'll talk about later. Others help us manage all the information about our project, the requirements, the designs, the data definitions, in one central place called a repository. They can analyze our designs to check for errors or inconsistencies, long before we write a single line of code. It's like having a robot assistant who double-checks your blueprints for mistakes. When it's time to actually write the code, programmers turn to their favorite tool, the Integrated Development Environment, or IDE. An IDE is like a super-powered workbench for a programmer. It includes a text editor specifically designed for writing code, with features like syntax highlighting that color codes your program to make it easier to read and understand. It includes a compiler or interpreter and a debugger, which helps them run the program step by step to find and fix those pesky bugs. Many IDEs also include visual designers that let programmers build user interfaces by dragging and dropping buttons, text boxes, and menus onto a form. How does information move through a system? Where does it come from? Where does it go? Who or what changes it? These are critical questions in the analysis phase, and the best way to answer them is by drawing a map. A data flow diagram, or DFD, is a simple picture that shows how data flows through a system. DFDs use only 4 simple symbols. Square, external entity. This is something outside our system that sends or receives data. Customer, kitchen, another system. Rounded rectangle, process. A process transforms data. Example, take order, calculate bill. Open-ended rectangle, data store, food menu, daily orders, arrow, data flow. The first diagram is the context diagram, or level 0 DFD. It's the highest level view, like looking at Earth from space. It shows our entire system as one single process with external entities. Customer sends order to system sends receipt to customer, system sends food order to kitchen. Now we zoom in, create a level 1 DFD by exploding process 0.0. Imagine opening the hood of the car. Inside 0.0, we have 3 main processes. 1.0, take customer order, 2.0, generate bill, 3.0, send order to kitchen. The customer order goes into 1.0, 1.0 looks up prices from food menu, 1.0 creates a new customer order in daily orders. We've just mapped the flow of information in our system. It's a powerful and simple way to understand and communicate how a system works from the inside.